Hello everyone and welcome to this week's OpenGL 3D game tutorial, and this week we're going to be optimizing the rendering of our particle systems using instanced rendering. So at the moment we're sending one draw call to the GPU for every single particle, which is not very efficient at all. The GPU can process huge numbers of vertices very quickly, but it can do this much more efficiently if it can process them all in one go, rather than only being able to process 4 vertices at a time before having to wait for the next draw call. What instanced rendering allows us to do is to tell the GPU with a single draw call to render the same vertex data multiple times. This can be used to render things like particle systems where the same model is rendered hundreds or thousands of times in the scene. The function that we're going to be using this week to carry out this instanced rendering is GLDrawArraysInstanced, which is exactly the same as GLDrawArrays, except it has one extra parameter which indicates how many instances of the vertex data should be rendered. Calling GLDrawArraysInstanced is exactly the same as calling GLDrawArrays in a for loop like this, which is very similar to what we're doing with the particles at the moment. But when the vertex data has to be rendered hundreds or thousands of times, the instanced rendering method can be much more efficient because it only requires a single draw call to be sent to the GPU rather than thousands. So with instanced rendering, we can render thousands of particles in a single draw call, but we no longer have the chance to update uniform variables in between each particle being rendered, which is a bit of a problem. Previously, we were updating the model view matrix between each particle render so that each particle could be rendered in its own position, and we also needed to update the texture offset and blend factor uniforms so that each particle could use its own part of the texture atlas. Without updating the model view matrix and the texture coordinate information, every particle would be rendered in exactly the same position, all using exactly the same part of the texture. So with instance rendering, we need a new way of being able to update the model view matrix and the texture coordinate information every frame. One way of doing this would be to make use of GLSL's inbuilt variable called GLInstanceID. This variable can be read in the vertex shader and it indicates which instance is currently being rendered. So when the first instance is being rendered, this variable would be 0, when the second instance is being rendered it would be 1, for the third instance it would be 2, and so on. For example, if I render a load of particles in the same position using instance rendering, but I add GLInstanceID to each particle's X position, then I'll get a row of particles like this, because for each instance that's being rendered, the GLInstanceID is incremented by 1, and so the X position of each instance is increased. So potentially what we could do would be to load up a giant array of model view matrices as a uniform variable before we even start rendering any of the particles, and that would contain the model view matrix for each particle in order, and then we could select the relevant matrix using the GLInstanceID variable. However, loading up potentially thousands of uniform variables to the shaders each frame would be rather inefficient, and I'm not even sure if it's possible, but there is luckily another way of doing it, and that involves storing all of the model matrices and texture offsets in the particle's VAO. If you remember all the way back to episode 2, a VAO contains data about each vertex in a model in attribute lists like this. The attributes can be accessed in the vertex shader using in variables, and the data being used in the vertex shader changes after each vertex is rendered. So when the first vertex is rendered, it uses the first set of attributes in the VAO, the second vertex uses the second set of vertex attributes, and so on, with the next set of vertex data in the VAO being used after each vertex has been rendered. If you remember, we stored data in the attribute list of the VAO from vbo's using the GLVertexAttribPointer method, where we indicate how many floats each bit of data has. So we might store a load of 3D positions in attribute list 0 of the VAO, and we would indicate that each position has 3 floats. And we might store some 2D texture coordinates in attribute list 1, and we would indicate that each bit of data uses 2 floats, and we might also store some normal vectors as well, indicating that each one requires 3 floats. Then during rendering, it iterates through the data for each vertex, moving on to the next set of data after rendering each vertex. When using instance rendering, it just repeats this process multiple times. So if you send an instance draw call to render 4 instances of this object, it would iterate through the data 4 times, once for each instance. So the attributes that we already have in the VAO are per vertex attributes because they change after each vertex, but it's actually possible to have per instance attributes as well, which change after each instance has been rendered. So imagine I send an instance render call to render this object 3 times. If I wanted, I could add some instance variables which would store data about each instance rather than each vertex, so maybe the world position for each instance and the colour of each instance. Obviously there are 3 of each here because I want to render 3 instances, but if I was rendering 100 instances of the object, then I would store 100 positions and 100 colours, one for each instance. When this is rendered using instance rendering, the per vertex attributes change after every vertex as normal, but the per instance attributes only change after each instance has been rendered. And this allows 3 different renderings of the exact same vertex data. So for the particles, there are a few things that we change per instance. Firstly, there's the model view matrix, which we need to change per instance in order to render each particle in a different position. Then there are the 2 texture offsets, which when we start coding we're going to merge into one 4D vector for convenience. And there's also the blend factor, which is currently one component of this text chord info variable, but we'll split this into 2 floats in a bit. So our particle VAO already has the vertex positions stored in attribute list 0, and they are per vertex attributes with 2 floats each. This episode we're going to set up some per instance attributes. So in attribute list 1 we're going to store the model view matrices for every particle that we want to render, and each 4x4 matrix will have 16 floats, and we'll also need to indicate that this is a per instance attribute. To indicate that an attribute is a per instance attribute, we simply have to call the GL vertex attrib divisor method and put in the number of the attribute that we want to be a per instance attribute, and the second parameter is always going to be 1, which indicates that the data should change after every single instance rather than after every 2 or 3 or 4, etc. Unfortunately though, the largest size that each bit of data in a VAO attribute list can be is 4 floats, so the 16 float matrices are actually going to have to be split over multiple attributes. So we'll split the 4x4 matrix into its 4 columns, and we're going to store 1 column in each of attributes 1, 2, 3 and 4 in the VAO. And of course we also need to indicate that each of these is a per instance attribute. We'll then store the texture offsets in attribute 5 of the VAO, indicating that each one uses 4 floats and that this is a per instance attribute. And finally, the blend factors will be stored in list 6, and of course the blend factors are only 1 float each. Of course, the model view matrix and texture information of the particles will be changing each frame, so we're going to need to update the data in the VAO every frame. We've previously always stored our data in separate VBOs, one for each attribute in the VAO, and if we were to do that this week, we would have to update each of these 6 VBOs every frame. However, there is actually a way that we can store the data for all 6 of these attributes in the same VAO, which would mean that we'd only have to update this single VAO rather than 6 different ones. So instead of storing all the texture offsets for each particle in one VBO and all the blend factors for each particle in another, we store all the data for each particle one after another in the same VBO like this. This is called interleaving, and now when we create the attribute lists in the VAO, we need to indicate which parts of the VBO they should get their data from. To create the attributes, we still actually just use the GL vertex attrib pointer method, but this time we're going to make use of the last 2 parameters, which we've previously just always set to 0. These last 2 parameters need to know the stride and the offset of the data. The stride is the amount of data in bytes that each particle uses, so this will be the same for each attribute, and in this case will be 21 floats, so 84 bytes. The offset indicates how many bytes into each memory chunk the data for the attribute can be found. So for the texture offsets, for example, this would be 16 floats or 64 bytes, and then the blend factors would be another 4 floats along, so their offset would be 20 floats or 80 bytes. So in this episode, we're first going to create an empty VBO. We're then going to link up the attributes in the VAO with sections of the VBO using the stride and offset parameters in the GL vertex attrib pointer method. We'll then indicate that these are per instance attributes by calling the GL vertex attrib divisor method for each attribute, and then we'll be able to treat these attributes just like any other VAO attributes, so we'll bind them to some in variables in the vertex shader, which we can then use just like we were using the uniforms last week. Then every frame we're going to iterate through all of the particles and update all of their instance data in the VBO that we created earlier, and then finally we can call GL draw arrays instanced to render all of the particles in one go. So first up this week in the display manager, we need to change the context that we're using to an OpenGL 3.3 context because we're going to be using some methods from OpenGL 3.3. Next up, we're just going to tidy up a few bits of code. from last week. So I'm just going to combine these texture offsets into one vec4 texture offset, which contains both texture offset 1 and texture offset 2. So texture offset 1 is now in the X and Y components, and texture offset 2 is now in the Z and W components. I'm also going to split the text chord info vec2 into two floats, and if you remember from last week, the two floats that contained were the blend factor and the number of rows in the texture atlas. So the blend factor was text chord info Y, and the number of rows was text chord info X. Finally, I'm just going to move these three uniform variables up to the top here, because these are the three uniforms that change per particle. So actually these aren't going to be uniforms anymore. These will be coming in from the attributes in the VAO. So now in the particle shader class, I'm just going to get rid of all of these locations for uniforms except for the projection matrix and the number of rows, because those are the only two actual uniform variables that we're still going to have. So we only need to get the location for those two variables, the projection matrix and the number of rows. And we don't need this method or this method anymore, but we do need a method which will load up the number of rows to the vertex shader. So just create a method that takes in the number of rows and loads it up as a float to that uniform variable. Let's now go into the particle renderer, and we no longer need to call the load texture chord info method, and we don't want to draw each particle individually anymore, but we do now need to load up the number of rows for each texture. So that line goes here, and I'm just going to cut out all of this texture code now, and I'm going to put it into its own method down here just to make things a little bit tidier, to make the code a bit easier to work with. So create a bind texture method which takes in the texture that we want to bind, and then you can paste the code back in there, and we're going to call the bind texture method up here in that first for loop. So that's pretty much all the setup stuff done, so we can now move on to actually implementing instanced rendering. And the first thing we're going to do is to create a big empty VBO, which is where we're going to store all the instance data for the particles, and then we're going to set it up so that the relevant attribute lists in the particles VAO get their data from the relevant parts of the new VBO. So let's go into the loader class, and we're going to start with the method to create a new empty VBO, and it's going to be empty because we're going to fill it every frame with new information for the particles, and this will take in the number of floats, the maximum number of floats that this VBO will ever have, because we're going to basically generate a big empty VBO of a certain size, and then we're going to fill it each frame with however many floats we need. So we'll start off by generating a VBO and adding it to the list of VBOs, and then we're going to bind the VBO so that we can use it. And this is a GL array buffer rather than a GL element array buffer, which would be for an index VBO. We're then going to allocate some memory to this VBO, and the amount of memory we need is the number of floats multiplied by the bytes per float, which is 4. So that will give us the number of bytes that we need for this VBO. And we're going to indicate that this VBO is going to be updated quite often, and to do that we add that parameter GL stream draw instead of GL static draw, which we've used before. Then we're just going to unbind the buffer, and we're going to return the ID for that buffer. Next up, we need a method that can add a per instance attribute to a VAO. So this is going to take in the VAO to which we want to add the attributes. It's also going to take in the VBO, which is where the attribute's going to get the data from. It also needs to know the attribute number, where we want to store the data. It needs to know the element size of each bit of data, like a 3D vector would have a data size of 3. It needs to know the instance data length, which is basically the stride, and the offset, which I talked about earlier. So first, we just need to bind the VBO and the VAO so that we can use both of them. So first I'm going to bind the VBO, which again is a GL array buffer, and then I'm going to bind the VAO. Now we're going to add an attribute to that VAO, and we can do that by calling the GL vertex attrib pointer method. This takes in the attribute number, which is attribute, the size of each bit of data, also needs to know the type of data that we're giving it, which are floats. Needs to know whether the data needs to be normalized or not. It needs to know the stride in bytes, so we need to multiply the instance data length by 4, and it also needs to know the offset, and it needs to know that in bytes, so we're going to multiply it by 4 because we're taking in those values as the number of floats. So we need to multiply them by the number of bytes per float, which is 4. And then we can just indicate that this is a per instance attribute, and it needs to be changed every instance. And now that we've done all of that, we can unbind both the VAO and the VBO. So just unbinding the VBO here, and now we can call GL bind vertex array and put in a 0 to unbind the VAO. So let's now go into the particle renderer and start setting up that VAO using the methods that we've just created. So here I'm just going to create a instance variable for the loader, which will just make things easier for us in a bit. I'm also going to create an int which is going to hold the VBO's ID so that we can update it every frame with the new information for the particles. We're also going to need to know the maximum number of particles that can be in the scene at one time, and I'm going to set that to 10,000, but you can set that to whatever you want. And we also need to know the amount of data for each particle, so the number of floats in the data for each particle. And if you look here, you can see that there's 16 for the model view matrix, 4 for the texture information, and 1 for the blend factor. So that's in total 21. So in the constructor, let's now create that VBO. So we're just going to create an empty VBO here using that create empty VBO method. And this needs to know the number of floats that this VBO should be able to hold. And that's obviously the number of floats per particle multiplied by the maximum number of particles. So instance data length multiplied by max instances. Next up, we're going to create some per instance attributes in the VAO, and these attributes are going to get their data from parts of that VBO that we've just created. So for each attribute, we're going to call the add instance attribute method. So we'll start with attribute 1, which is going to be storing the column A's of the model view matrices, and each of those columns has 4 floats. The stride is just going to be the instance data length, and the offset for the column A's is going to be 0 because they're right at the start of the data. Then for the other 3 columns, we're going to store them in attributes 2, 3, and 4. These all have 4 floats as well, but for each one, the offset is going to be increased by 4 because each one is 4 floats further into the data. Then in attribute number 5, we're going to be storing the 4D texture offsets, and these have an offset of 16, as I showed earlier. And finally, in attribute 6, we're storing the blend factors. They're all 1 float each, and they're going to have an offset of 20. So now, just like any other attributes in a VAO, these can be accessed in the vertex shader as in variables. So we need to change these 3 uniforms to in variables, and we now need to link those 3 in variables with the relevant attributes in the VAO. So the model view matrix in variable, and make sure you spell this the same way as it was in the vertex shader, that started in attribute 1 of the VAO. The texture offsets were stored in attribute 5 of the VAO, and the blend factor was stored in attribute 6 of the VAO. And then the final thing we have to do, and I always forget to do this, and it always takes me a while to realize what I've done wrong, but you have to remember to enable the attributes before rendering so that they can actually be used during rendering. So enable attributes 0 to 6, and in the finish rendering method, this is in the particle renderer, we need to disable all of those attributes 0 to 6. So let's now go into the loader class and create a method that can update a VBO with some new data. So I'll create a method here called update VBO. This is going to take in the VBO that we want to update and the data that we want to store in it. And it's also going to take in a float buffer so that we can reuse the same float buffer every frame instead of creating a new one each time, which would be a bit slow. So the first thing we'll do is we'll clear the buffer of any previous data. We'll put in the new data, and then we're going to flip the buffer so that it's ready for reading instead of writing. We then need to bind the VBO so that we can do stuff to it. And again, this is a GL array buffer VBO. And we're then going to actually reallocate memory to this VBO in the exact same way that we did back in the method to create the VBO. And the reason we do this is that it makes it a little bit quicker to store new data into it, because it basically tells OpenGL that it can completely forget about any previous data that was in the VBO, so it doesn't have to worry about keeping that updated. We're then going to store some new data in the VBO using GL buffer subdata, and this needs to know where we want to start adding the data, and I'm going to put a 0 there to show that we just want to start adding the data at the beginning of the VBO. And we're then going to unbind the VBO because we're finished with it. So in the particle renderer, we now need to have a float buffer that we can reuse every time, and we're going to initialize this float buffer and by calling create float buffer, and we have to put in the size of the float buffer, and again this is the number of particles multiplied by the number of floats needed for each particle's data. And we're also going to create an int variable here so that when we start storing the particle data in a float array, this will indicate where in the float array we're currently writing to, and we need to reset that pointer to 0 before every particle list. I'm just going to tidy the code up a little bit here, so I'm going to get the list of particles that we're about to iterate through by doing particles.getTexture, and we can then substitute that in here. So we now need to create a float array, and we're then going to fill that float array with all of the data from the particles in the list. So we'll iterate through the particles and we'll fill up this float array with all the instance data. And the size of this float array needs to be the number of particles multiplied by the number of floats needed to store the data for each particle. So that's particle list.size multiplied by instance data. So when we iterate through the particles, we need to store all the information for them in that float array. So the update model view matrix now takes in that float array, and instead of loading the model view matrix to the shader, we now need to simply store it in that float array. So I'm going to create a method to do that, which is going to take in the matrix that we want to store, which will be the model view matrix, and that float array of data. And I've actually got this copied and pasted because it's quite annoying to type all that out. And you can copy that from the description if you want, or if you do copy it out, make sure that you get all those numbers correct. But basically that just stores each of the columns of the model view matrix into the float data, and then we're going to call that method from the end of the update model view matrix method. So every time, for every particle, the model view matrix gets updated and then stored into that vboData float array. And of course, we also need to store in that float array the data about the texture information, or the offsets, and also the blend factor. So let's create a method to do that. That's going to take in the particle and that float array data. And if you remember, the first thing we need to store is the offsets, offset 1 and then offset 2. So first offset 1.x, then offset 1.y, and then we need to store offset 2. So offset 2.x, offset 2.y, and then finally the last bit of instance data is the particle's blend factor. So store particle.getBlend, and we're going to call that for each particle after we've stored the matrix information. So once we've iterated through all of the particles, we'll have all of the particles' instance information in that vboData float array, and we can now update the VBO with that data. So let's put in the vboData, and the buffer that we want to reuse. And now that the buffer has been updated, we can actually draw all of those particles using GL draw arrays instanced. And this is exactly the same as GL draw arrays. So it takes in triangle strip 0 and then the number of vertices, which is still quad.getVertexCount. But it also needs to know the number of particles that we want to render, and that's going to be particle list.size. So that is now it. And if we go ahead and run that, hopefully it will look exactly the same. But you can be happy in the knowledge that those particles are now being rendered a lot more efficiently. So that is basically it for instance rendering and particle effects, but there are just a few more things which people have suggested in the comments which could improve the efficiency of the particle systems. Firstly, we're creating a lot of objects each frame, such as vector 3fs, and for very large particle systems this would mean tens of thousands of new objects being created every frame. This isn't exactly the most efficient thing to do, so it might be a good idea to consider reusing instances of vectors and just setting their x, y, and z components each frame, rather than creating a brand new object each time. You could also do a similar thing with the particles themselves and just reset the variables in a dead particle object rather than creating a new particle instance. Each particle system could have a set amount of particle objects allocated to it when it's created, and then you would just reuse the same objects using a Boolean flag to indicate when a particle is dead, and then just resetting the variables in a dead particle when a new particle needs to be created. And the last thing is that you only need to sort particles which use alpha blending, because as I mentioned last week, additive blending is order independent. So that is it for this week. Next time I think I'll be doing a quick tutorial about procedural terrain generation, and then after that we'll get started with shadows, which will probably take about 2 or 3 episodes. But yeah, thank you guys very much for watching this video. Do subscribe if you haven't already. I hope you all have a great start to the new year, and I will see you all next time.